TemperIt, an automated chocolate tempering machine.
So what is chocolate tempering? Chocolate tempering is the process of melting chocolate and cooling it to reform the crystals in a uniform way. It uses constant mixing and accurate time intervals to uniformly break the crystals in the cocoa butter. You also do what is called seeding the chocolate, where cool chopped chocolate is added at set intervals to the melted chocolate to aid in cooling. It produces a glossy finish and a nice snap to the chocolate when broken.
Here you can see a timeline of the project. We ended up spending more time studying and clarifying the problem and generating solutions than anticipated, which pushed us a little bit behind schedule. But this allowed us to really understand the stakeholder needs and test many different solutions.
One of the first steps we took before solution generation was to identify the core stakeholders to frame the context of our design. Other than the inherent stakeholders such as the team and the IGEN 230 professors, we identified 5 primary stakeholders. A successful implementation of our product would offer home chocolatiers and aspiring home cooks an easy gateway into automated chocolatiering. In addition, our product would provide a more economic solution to automated chocolate tempering for current professional chocolatiers. In order to derive valuable target design specifications, we first needed to identify the needs of the stakeholders. To do so, we reached out to 20 local chocolatiers as well as home bakers, so that we could both better understand the market and the issues faced by our stakeholders. We determined full automation, the ability to fit as a household kitchen appliance, ease of use, affordability, and ease of cleaning to be the primary stakeholder needs.
We determined our requirements using our stakeholder needs. The objective of our design was to produce a device that comfortably fits within a kitchen as a home appliance. It should be intuitive to use and must temper chocolate properly. The device should also hold a minimum of 1 kg chocolate and should read the temperature of the chocolate mixture accurately at all times. However, as a result of COVID-19, we were unable to fulfill many of these requirements. We did not receive the acrylic sheets, the IR temperature sensors, and the push buttons. We also did not have access to the laser cutter. This in turn impacted our requirements. The device could not be made entirely food safe as we did not have access to our acrylic sheets and had to rely on our 3D printed prototypes. The device size could not be determined as we did not build our chassis due to lack of access to our acrylic sheets and the laser cutter. The temperature control and accuracy was affected because of a few temperature sensors that did not arrive on time. Although we were able to complete the software that would allow the user to select whether they wanted to temper milk or dark chocolate, the buttons that we had ordered did not arrive on time, and thus we could not physically implement the code.
Before we discuss our project in detail, here's a preview of our final prototype. Initially, we brainstormed 3 different heating methods, which included a double boiler, a direct heat surface, and a sous vide heating system. The double boiler and sous vide system did not make the final design due to the significant added technical complications of including water in the heating method. This resulted in requiring a bowl removal mechanism, as well as a pulley system for the sous vide heating system. The direct heat method scored the highest in the WDM, as we were able to easily control the heating of the chocolate by varying voltage inputs to Peltier chips, which can heat and cool the chocolate at specific temperature intervals. We split the team into 4 different subteams. The stirring mechanism is required to mix the chocolate evenly to ensure even distribution of heat around the chocolate and refrain the chocolate from burning. The hopper system adds chocolate at consistent intervals during the cooling stage of the full chocolate tempering process. The chassis is an acrylic construction which integrates the bowl as well as electrical and mechanical components. Finally, the electrical system focuses on providing heat to chocolate with Peltier chips and controlling the distribution of heat at given temperature intervals.
The stirring mechanism ensures that the chocolate in the bowl is heated and cooled uniformly by maintaining a constant motion. Our main requirement was that the stirring mechanism efficiently scrapes the sides and the bottom of the bowl. We had several ideas for our stirrer head, and to decide upon our final idea, we used the WDM. The trapezium received a high score of 8.9 and was chosen as our final design. Our final stirring mechanism consisted of 5 main parts: the motor mount, the motor coupler, the shaft, and the stirrer head. The motor mount was used to keep the motor in place. The detachable C in the middle of the mount helps to detach the motor during disassembly. The stirring head was chosen after a careful analysis during the WDM. It was made to fit exactly into the pan so that it scrapes the entire surface area of the pan. The edges were curved for cleaning purposes. The empty trapeziums in the middle helped chocolate to flow freely without rising against the stirring head.
The motor coupler went through 2 rounds of extensive prototyping. It is designed with a rounded fillet to reduce stress concentrations and uses M2 mounting bolts with a 6-32 fastener. After designing the coupler, we got it machined by the material shop. We decided to use a rectangular 1/4 inch aluminum sheet metal shaft rather than a rod shaft, as it is the easiest to couple to a laser-cut acrylic stirrer head. The motor coupler is designed to reflect this, such that the stirrer head is aligned with the center of rotation from the motor. This is the subassembly of the stirring mechanism. It mounts directly overhead the chocolate bowl. On the right, you can see our functional prototype. We were unable to complete the full assembly of the subsystem in real life, but the left picture shows what it would have looked like.
The hopper is how we seed the chocolate, dropping cold chopped chocolate into the already melted chocolate at set intervals. Our final design is pictured here in these CAD models as these 3 interconnected slats that create 6 different segments to be able to be filled with chocolate and then dropped in. Once we received the servo motor to be used with the hopper, we designed this motor coupler to allow the servo arm to be attached to the different slats of the hopper and rotate it. We also designed this motor mount as to mount the motor on the chassis just above the hopper to allow free rotation of the hopper without rotating the motor. Unfortunately, due to COVID, we were unable to create these final designs. However, pictured here are CAD models of what we would have created had we still had the resources.
The chassis design utilizes interlocking acrylic sheets to create the general structure. The acrylic sheets are laser cut, and cutouts are made in the 3 horizontal layers to mount the electronic and mechanical components. To provide support, threaded aluminum rods are bolted in the 4 side corners of the chassis, and interlocking teeth are held in place with acrylic adhesives.
For the electrical component of this project, we built the circuit shown in the circuit diagram. We used Peltier chips as a voltage-controlled heat source, and an 8-channel relay module to control the Peltier chips and our 2 motors, one for the hopper and one for the stirring mechanism, using PWM. We used a contact temperature sensor for our feedback loop, although we had intended to also add 2 IR sensors for greater accuracy, as well as 3 push buttons for user input. We used 4 TEC1-12706 Peltier chips in direct contact with the bottom of the pan for heating, with our contact sensor in the middle of the 4 chips. In order to supply enough power for all of the circuitry, we used a power supply unit, or PSU, generally used in computers. This worked as a transformer and allowed us to draw power from a wall outlet without damaging our sensitive circuitry. An advantage of using the PSU was that it had multiple output pins which supplied different voltages. In order to determine which pins were to be used for each component, we first performed power calculations. This array of outputs allowed us to easily and consistently supply each Peltier chip with the 5 volts needed, power our high-torque stirring motor with 12 volts, as well as power the Arduino and the hopper motor.
This is a state machine for the chocolate tempering machine. It detects whether the user has selected the type of chocolate and begins the chocolate tempering process when a type of chocolate has been selected. The chocolate tempering process consists of 3 main phases: the heating stage, cooling stage, and tempering stage. The machine completes these stages by detecting whether the temperature of the contact sensor has reached the bounds of each process. In its implementation of this into code, we have assumed that the reading from the contact sensor is equivalent to the chocolate temperature. We were unable to conduct testing to find the relative temperature of the chocolate compared to the reading of the contact sensor. The chocolate tempering machine also has two main safety features. First, there is an LED indicator displaying whether the chocolate tempering process is in place. Secondly, there is an emergency stop button to stop the tempering process. We transformed the state machine into Arduino code, which integrates Peltier chips, servos, motors, an LED, and a contact sensor.
This is our final SolidWorks assembly. It gives a layout of how we planned out our subsystem integration. As you can see from the top view, the hopper system is mounted using interlocking acrylic and the stirring subsystem is mounted with screws. The chocolate pan fits within the circular cutout and the Peltier chips fit underneath in the square cutouts. Below it, the Arduino and the corresponding electrical subsystems can be mounted to the side walls of the acrylic chassis.
In conclusion, we believe our product would be very beneficial to stakeholders as we've kept them in mind throughout the process, and we're hoping to be able to finish the device when we regain access to the necessary resources. We hope to complete testing, and our objective in the future is to be able to accommodate more stakeholders by scaling up our project and tempering more chocolate. We want to make chocolate tempering and chocolatiering a little bit more accessible for everyone.